Okay. So once you make measurements, what we want to do, so when you do labs, um, and you write down numbers, you want to be able to interpret those numbers in terms of what's happening in the experiment, and these numbers will help us figure out how good the experiment is and how close it is to what we expect. And so this relates. And I always like using this scenario here. Let's say I have some sort of shooting range. There are 4 people shooting. I have first person, second person. Put 2 here. And then there are 2 things I'm going to look at. I'm going to look at how close they get to the bullseye and how repeatable the shots are. Okay. The first part I'm going to relate to is accuracy, is how close they get to the bullseye. And the second part is called precision, how close their shots are together. So we're going to score all 4 of these guys in terms of both of those. So number 1 guy comes up, and I don't know, it could be bullets shooting at a target, and takes 4 shots. And I ask, how accurate was this person? How close did they get to 0? And I'd say they're not very accurate, because none that are real close. How good are the precision? No, I'd say not very good, because they're not close together. Well, they're all close together in terms of the target, but we're going to make these guys not very good at precision. Their 4 shots are off from each other. So, not very good accuracy, not very good precision. Okay, number 2 person comes up and takes his 4 shots. Now we look at the accuracy. And this person doesn't have very good accuracy. It doesn't get close to bullseye. But this person is very good with his precision. Okay. Okay, number 3. Okay, comes up, takes shots, and hits all 4 of them. 4 bullseyes, very good accuracy, and very good precision. Number 4 comes up, shoots, hits the bullseye, drops the gun, and goes, I'm done. I'm really good. Okay. How's their accuracy? Well, good. How's their precision? We don't have any idea, because they didn't take another shot. Okay, so what we want to do is look at all 4 of these. Okay, so again, shooter 1 doesn't get close, low accuracy, low precision. Would say that they're bad for both. Okay, so bad accuracy and bad precision. Number 2, again, low or bad accuracy but good precision. Number 3, good accuracy and good precision. Number 4, good accuracy, but we don't have any idea about precision, so it's bad precision. So we would graph this. Okay. So number 1, bad, bad. Number 2, bad, but good precision. Number 3, good, good. And number 4, good, bad. So our obvious question is, which shooter is the best? Well, if you define how good the shooter is by hitting the bullseye and precision, you'd pick number 3. But number 4 is pretty good too, because they hit the bullseye. Okay, the problem with number 4 is which one of these 2 would you trust? Okay, would you trust number 4 or number 3? Okay, well, if you pick number 4, you don't know where the next shot is. This might have been just a lucky shot, and next shot goes way off and kills somebody. Okay, this guy over here, you're pretty sure is going to get both. Okay, now how about, obviously number 1 you don't want to work with them. Number 2 is a different story. Okay, even though they're not accurate, okay, I would be willing to work with number 2 way better, more than I would work with number 1 or number 4 because of their precision. Okay, number 1, there's no, I mean, it might take a long time to really help fix their things. Okay, maybe you'll never fix it at all. Number 4, you don't even know. They've walked off because they think they're the greatest shot ever. Number 2, well, I mean, in terms of a gun, it might be the sight. Okay, so the accuracy, maybe all you have to do is adjust the sight. Okay, maybe the person just has to, maybe he's aiming with his right eye instead of left eye or something like that, and so you can fix that problem really quick. Okay, so this is actually good information. You can work with this one right here and get, because you got information from it. Okay, you know that they are precise, and then maybe what you can do is fix the accuracy. Okay, so number 4, okay, number 4 might be good, but only one shot, you can't tell. Okay, when we do experiments, we're always looking to get reproducible results. First, not what the right answer is. If you do an experiment once and you get the right answer, it doesn't mean anything. Okay, it'd be better to get the wrong answer over and over, regardless of what the definition of insanity is. Okay, remember that. Is doing the same thing over and over and never getting it right is insanity, or you're always getting the same answer. Okay, so that's not what we're doing here. If you get the wrong answer over and over and over, it's telling you something. It's telling you some information. Okay, it's telling you that maybe something needs to be fixed. If you only do the answer probably once and you get it right, it could just be plain luck. Okay. So again, accuracy is how close one gets to the expected results, and precision is the lack of error in the experiments, which are reduced by many things. Getting the same over and over, answer over and over, having good measuring equipment, having good protocol, reducing variables, and all that. Okay, here's some examples I've seen in experiments. Scenario number 1. In many typical science classes, you will do an experiment that will have a supposedly correct answer. So here's an example. And this one I had many years ago. Students do a lab and the answer is supposed to be 1. And this is one I did where we were supposed to get the density of water was supposed to be 1 gram per milliliter. And if you got 1, you got 10 points. And if you got another answer, you got to reduce score, maybe 8 out of 10, because you didn't get an accurate enough answer. Okay, well, when I did this lab, out of the 30 students, only one person got 1 gram per milliliter. The rest of them got around 0.85. Okay, now naturally that one student was jumping up and down saying, "Hey, I got it right, you guys are all wrong, I know how to do it better." But the problem is that the right answer really is 0.85 because it's reproducible. Okay. All right. Okay, so everybody used the same equipment. Okay, so all these scales were exactly the same. At least I think they were, and that's what I thought at the time. And so what value is better? The 1.0, the expected answer, or the majority answers? Okay. If you decide this should be 1.00. If you decide it's 1.00, you are only looking at the accuracy. Okay. All right. And this would be like shooter number 4. I got best shot. I got a 1. I don't have to do anymore. I got 10 on the scale. Well, the best answer really is 0.85. Okay, even though it's wrong, it's the right answer because it's the most precise. Okay, so this is the one reason that when students come up to me and say, "Dude, does this answer look right? Does this answer look right?" I never like answering because I don't know. I mean, maybe the answer is right in terms of precision, and maybe it's wrong in terms of accuracy. Okay, so whenever you do an experiment, what you do is you do the experiment. You don't worry about what your answer is. You just try to do the experiment right. When we ended up doing this, I had to believe that the that the precision 0.85 tells me that something was off, and I found out that actually the scales were off, and they are all really giving me an incorrect value for water. Okay, and actually I was able to fix the scale so that we'd do that. So I got some good information, even though it was inaccurate. So what is important here is not to worry about getting the right answer. Okay, it's about being reproducible. If I would have given students 8 points for having the wrong answer, even though it's wrong not because of what they did, because of the equipment, that'd be wrong. Okay. And I know many teachers, many teachers that just grade on accuracy and expect the experiment to give the result that's there, but you can't assume that. So whenever you do a lab, you always should look at describing the precision of the experiment before you even talk about how close the answer. If you do an experiment only once, technically you can't be sure about your results. If precision is not good, no matter how good your answer, the experiment may be flawed and the information that it gives. Okay, so when I'll be doing the labs for you guys, and I'm only going to do them once, I think. Okay, so you're going to have to assume that there's always going to be some sort of lack in precision in my results, and I'll be talking about those as I do the lab. Just have to pay attention to it. Now, hopefully, if I end up getting a number when I do the labs that's very inaccurate, okay, then what I'll probably do is I'll probably redo the experiment, and if it comes up with that same inaccurate number, then we'll discuss that. All right. But if the answer is fairly accurate when I do the experiment, I'm going to assume that it's close, that that I'm okay. Okay, but I still can't fully assume it because of precision. This is why it would be really good if we all could be doing experiments. What we'd like to do is compare everybody's results, and then we could get precision. And that's what we get here. So it turns out when we do labs, you only do the experiment once, and that's really not a good way of reproducibility. However, there's another way around it. If all the students in the lab are doing the same experiment with the same equipment, we can kind of think of this as, instead of having 20 students do 20 individual experiments, we can kind of think of it as one experiment being done 20 times. And that's because all of you will be doing basically the same kinds of minute errors in measurements, and the equipment is also going to have the same errors. And so you kind of incorporate and believe that you're all just one student and all the equipment is the same. And so what we can kind of do is just sort of assume that the 20 20 experiments done individually is the same as doing one person doing it 20 times. And since we do this, if we find that after doing an experiment that most of the students got the same answer, then the precision is good. And that's actually what I like to do, is I like to go over everybody's results, decide if the answer is precise or not, and then what we do is we go over and see how it compares to the accuracy. For instance, you know, suppose that everybody gets quite different answers. Okay. If everybody gets quite different answers, then basically the experiment's imprecise. And you can't, even though some people might have got the right answer, it doesn't mean a thing because the experiment is imprecise. Okay, when we do labs, of course, your number one job is always to do the experiment as well as you can without worrying about if you get the right answer. What I do is not even talk about the expected answer until after the lab is done. Like I said, students are always coming up to me, is this close to the answer? I'll just tell them, I don't know. Okay, we'll find out later, because we have to decide if the experiment is precise. What you always have to do, your job in the lab, is to write down your results, okay? And what you reserve is not to study how close it gets to the answer and worry about it's wrong. You know, a lot of students, if the answer is 5 and they're told the answer is 5 and they get 2, they're saying, oh, I'm the world's worst student. Okay, well, their neighbors also get a 2 and they go, well, I'm really bad, and their neighbor gets 2 and they go, oh, we're really bad. And once one group gets 5, okay, they're really good. I'm going to trust this group over here, not this guy over here. All right. I will not tell you if you got the right answer, because what you have to do is do the experiment, decide if it's precise, and then move on. And that ends this. Okay. And as I do labs and I present them to you, we'll talk about the precision and accuracy of the experiment.